Hello everyone, welcome to Artificial Intelligence and MSE, the second installment of the 6-part outreach webinar series organized by the Department of Material Science and Engineering at NUS. Consistently ranked among the top globally by Times Higher Education and QS, MSE at NUS has made extensive contributions and breakthroughs in research, education, and innovation, clinching numerous awards, both locally and internationally. With cutting-edge research in areas such as advanced manufacturing, bio-inspired materials, edge computing, and computational material sciences, as well as world-renowned faculty members such as Nobel laureate Professor Konstantin Novosel, Prof. Silvia Garacek, and Prof. Barbaros Ozimas, it is almost unsurprising that MSE at NUS is one of the leading MSE departments in Asia. I'm Fadila, the moderator for today's webinar series. Before we begin, let me briefly introduce the Outreach webinar series. Organized in conjunction with the MSE Roadshow, the 6-part webinar series aims to raise awareness and showcase the diverse roles and career opportunities available to MSE graduates. Over the next few weeks, several distinguished speakers from various fields will each give a talk on the career pathways they have embarked on. For a more interactive experience, the webinar will be split into 2 parts. The first being the talk by the invited speakers, followed by the Q&A session, where the panel, comprising of the speakers, as well as Associate Professor Daniel Blackwood, Deputy Head for Education and Student Affairs at MSE, will answer questions posed by members of the audience. Members of the audience may submit their questions in the webinar Q&A and indicate if they would like a specific speaker to answer their question. Do also remember to complete the survey when prompted at the end of the webinar. To kick off today's session, I welcome Associate Professor Daniel Blackwood, Deputy Head for Education and Student Affairs, to give the opening speech. Prof. Blackwood, please.
Thank you. Okay, if I can share the screen. Oh. Okay, thank you for coming. I'm going to give a basic introduction to the department, and then our next speaker, Stefan Adams, Professor Stefan Adams, will talk more about AI in particular. Okay, so we're the Department of Material Science and Engineering at NUS, which obviously, hopefully by now you would know. A few things about why you should come here. We're actually the first department in the world, or the first in the world, to have a dedicated institute on functional intelligent materials. It's a university institute, but all the professors are linked to our department. I will say a little bit more about that in a moment. As far as world rankings are concerned, we're ranked 5th in the world. So that's not 5th in Singapore, that's 5th in the whole world in terms of material science and engineering departments. And perhaps importantly, from your point of view, if you're going to be a student with us, when it comes to getting a job after you've graduated your degree, whether that's at the bachelor or the master's level, the employer reputation, we're #1 in Singapore and indeed #1 in Asia. So employers like our students, and that's important from your future point of view. We're also the only department in the whole of Singapore to have a Nobel Prize winner, Professor Sir Konstantin Novosel. He joined us a little bit over a year ago, and he came to NUS because he sees us as a forward-looking department where he can further develop his ideas, and he is the founding director of this new institute. Okay, so what is material science and engineering? I'm aware that most of you, the JC, sort of know what chemical engineering, mechanical engineering is, electrical engineering, but may not be so well aware of what MSE is. Well, what we do is we take all the primary sciences, chemistry, physics, biology, and we sort of combine them all together, put in some engineering to design materials for future applications, whether that's energy storage, batteries, solar cells, biomedical devices such as stents, 2D materials, graphene, it's great for electronics, or even soft materials in robotics, the feeling of touch, right? How do you pick something up? It's It's easy for you to pick something up, but it's not actually very easy for a machine to know how much pressure it needs to pick something up. It needs a sensor, and it needs a material that can sense that. So if you're very interested in science, so during your JC days, if you like physics, chemistry, or biology, but you want to do something with it that in the end will matter rather than just being science for science sake, then material science and engineering is the degree for you to choose. And our employment rate has been good. This was the 2019 survey, which was published in 2020. Next month, I believe the MOE will actually produce another survey. They tend to bring it out every February. But last time, even though it was COVID, we still had over 90% of our students found employment within the first 6 months. Salaries were reasonably good as well. The mean is at $3,922. The medium, a little lower, but virtually the same, right? This is in the noise level. And our top students are getting over 4,000. Okay, so we're above average in engineering salaries if you're doing material science and engineering. Indeed, if you go into AI, which is what this talk is about, you're more likely to be in this area. This doesn't mean our top students, top CAP students, this is the top earner students. There's more to getting a good job than just exam results. Okay, it's part of your personality. Have you done the right specialization, things like that. All right. And so onto specializations. We already have 2 specializations that we've had for quite a long time, one in polymers. Polymers is a fancy way of saying plastics, but there's a lot more to it than your shopping bag. Polymers are used a lot in the biomedical industry, artificial valves, biological body replacements are mostly made out of polymers. We also have nanotechnology for quite a long time. That's a lot to do with the electronics industry. But we're also launching 2 new specializations. One is on artificial intelligence, or related to artificial intelligence. That is being passed by the university and just needs MOE approval. So that will certainly be ready for when you join us in the summer. And the next specialization we're working on is biomedical materials, and that's been passed by most of the university, just needs Senate approval and then MOE. So when you come and join us, there'll be both biomedical material specialization, and importantly for most of this audience, we're having a specialization related to artificial intelligence. This is one student I'd like to mention, Vishnu. He's actually graduated in the 2019 cohort, and he set up an AI company. He's basically in health and safety. So he's using AI to improve companies' health and safety. So he's one of our recent graduates who's used his experience in MSE combined with AI knowledge to set up his own company. And the company's doing very well at the moment. A little bit more achievement about our research side. We actually have 5 researchers that are amongst the most highly cited researchers in the world. Okay, worldwide, the citations are right. We do our research, we publish papers, and if other people find our papers useful, they will mention our papers in their own papers. So that's what a citation is. Worldwide, they list the top 6,600 of these top researchers, and in NUS there are 32, of which 5 are in MSE. So although MSE is only a relatively small department, we have maybe 30 academic staff, maybe. So that's I don't know, maybe 10% of the faculty of engineering, and yet we've got more than 10% of the top researchers not in the faculty, but actually in the university. So that shows how well our standard is compared to the whole of the university, and NUS is a very good university. So you'll be learning from the best. We've also just started, or the university has just launched a new research institute in functional intelligent materials, which is based on using AI to produce new materials with specific applications. Although that's at the university level, it's got very strong collaborations with MSE, because all the founding professors, as you can see from the list below, all 5 of these are members of our department. Barbaros is our head, Costina is our Nobel Prize winner, but also Antonio and Dario and Marcic are all part of our department. So it's the world's first research institute on functional intelligent materials. It's over $200 million investment over 10 years, so that's a lot of money. And they will be employing researchers and PhD students, approximately 100. So it's 10 years, so you join us now. In 4 years' time, you will graduate with your bachelor's degree, or in 1 or 2 years' time, if it's a master's degree. And then you have a chance to do a PhD in this institute. Okay, this is only one of a number of events that we're holding. So I'll give you a little time to scan the QR code of other events if you might be interested in. Last week, we had an event on women in MSE, so we'd like to encourage the girls to come to our department. I know many go into biological areas, but MSE is very important in the bio area. So we'd like to encourage you. Engineering has always been short of females, but females do very well in engineering. So we'd like more to come in. So now we're at AI. We will soon have one on electronics, then one on biomedical materials, on sustainability, and finally an alumni sharing. But you can see from these topics, right, electronics, sustainability, biomedical, AI, how important materials is across the whole field of engineering, science and engineering. That's why it's such a good choice for your option to do your degree. You don't corner yourself into one specific small area. You have a lot more options for your future career. And this one is also for admission, so I'll let you scan that if you want. The QR code for undergraduate admissions is this one here. And if you're interested more in MSE as a whole, you can scan the code for the MSE interest group. And after you've joined that, you can ask any questions you like to the interest group. This includes some of our students and alumni who can give you a more direct answer than maybe the professors would. Okay, so that's my last slide. So I will stop sharing and hand back to Farella. Okay.
Thank you, Prof. Blackwood, for the very nice talk. In today's webinar, we are fortunate to have with us 2 individuals who are very well versed in the domain of computational material sciences. They are Dr. Yu-Heng Lee and Associate Professor Stefan Adams. Welcome to today's webinar session, and thank you for joining us. First up, we have Dr. Yu-Heng Lee, a Bachelor's of Material Science and Engineering graduate from Zhejiang University, China. Dr. Lee did his PhD on hybrid halide perovskites for photovoltaics and light-emitting applications in the University of California, San Diego, USA. Now, a postdoctoral fellow in MSE and NUS, Dr. Lee's research work focuses on the fundamental understanding and rational design of novel materials for advanced energy storage systems via materials modeling and high-throughput computational studies. Dr. Lee, please.
Thank you for the introduction. Let me share my screen. All right. Good afternoon, everybody. Today, I'm glad to talk about the applications of artificial intelligence in material science and engineering. So materials are fundamental in all kinds of applications in our lives. We can see metals, ceramics, polymers. Oh, sorry, I forgot to start the video. Sorry about that. So materials, we can see in our everyday life, metals, ceramics, polymers, etc. And for functional applications, materials are also fundamental to computer chips, displays, and batteries. So the advanced materials that's under active research are the key enablers of innovative technologies. For example, here we have the advanced structural materials, like the recently developed moldable wood. There are also super hydrophobic materials for waterproof applications. And we have the nanoparticles that can be used for drug delivery and can be directed to the cancer cells. There are also self-assembled nanorobots that can be put in our blood veins. Also for health-related applications are the soft electronics, which can be made into wearable devices that can, for example, monitor our blood pressure. So one of the most important application for materials is to facilitate renewable energy. As this sketch shown here, we have the energy conversion applications like solar cells. So the solar panels made from materials can absorb light and convert them into electricity. There are also the energy storage materials for batteries or electric vehicles, and also catalytic materials for hydrogen oxygen generation and carbon dioxide conversion and capturing. So now we have an idea of the materials role in our everyday life and the more advanced applications. I'd like to briefly introduce how materials research is conducted. So let's focus on the blue boxes. On the left are the inputs and on the right are the outputs. There are 3 generations, and the 3rd generation referred to artificial intelligence. We can see clearly the inputs for artificial intelligence are more simple and basic chemical and physical data. So it doesn't necessarily require any pre-knowledge of the materials being studied, like the material structure or materials composition. And for the output, the artificial intelligence can give us even more information than the first 2 generations. So one major topic in the materials research is to design and discover novel materials. So for many years, this has been done following the traditional Edisonian approach, which relies solely on the experimental trial and errors. So it's very time consuming. In recent years, much advanced approach is the high throughput approach. This is usually based on calculations, which means the quantum mechanical modeling, which can give you materials property on computer based on physical laws. Of course, there are also high throughput experiments. So the advantage of this high throughput approach is that it's highly automated and accelerated. And thirdly, we have the topic of today, artificial intelligence. It can again greatly reduce the time and the cost of design and discovery of materials. And it can extract useful information by itself. It can even discover hidden laws that might escape human eye. So it has been, the big data plus artificial intelligence has been referred to as the 4th industrial evolution. So you get the idea how much advancement that is. So within the field of artificial intelligence, one of the most popular and most important subfield in recent years is machine learning. On the right, the figure shows a workflow for building machine learning models. So it is based on data, and the white arrows show the data flow. So from data, we can do feature engineering, which is used to train the machine learning model. And finally, we can do analysis, which in return can improve these 3 steps. So the machine learning model basically, it's from statistical models and optimization algorithms. You can simply understand it as a highly sophisticated curve fitting. The machine learning can reveal patterns in the input data to make decisions and predictions. And machine learning is especially valuable for cases where something is too slow or difficult to obtain by human efforts, or for relationships that's beyond our understanding at this moment. So here I give a real-world example of what machine learning is capable of. So in this study, the researchers have taken many of these railway track pictures, and by marking these different components, they taught the machine to learn to identify the different components in such a picture and do the railway track inspection. So after the machine learning model is trained, it can conduct materials classification and degradation detection in thousands of such pictures in just a few seconds. So you can imagine if you hire some consulting company to do this, what's the time and cost difference between the machine learning model. So now we're familiar with material science and we're familiar with artificial intelligence. So what happens when we apply machine learning in material science? So here is a very comprehensive graph showing how to construct machine learning models for materials. So it is basically the same machine learning workflow we just saw that's filled with material-specific contents. So first, we want to identify the purpose and target of our study. This is referred to as the domain knowledge. In our case, it's a material science knowledge. For example, we want to find a faster ion conductor for battery materials. Then, as we know, machine learning models are based on data. So we can first either to generate the data from the existing materials databases, or we can collect data by ourselves using these automation tools for high throughput computations. So with the data, we can do feature engineering. There are also built tools out there for feature engineering. And for material science, the features are usually based on the more basic properties like the elemental features or structural features for the material. Then after the feature engineering, we can do machine learning model training, which is based on different algorithms. And there are tools out there. Of course, these are not material specific, like scikit-learn, TensorFlow, and PyTorch. And finally, we can do the application, which is to make decisions or predictions about the materials. So following this, I will give some more detailed introduction to some of these steps and give some practical examples for applying machine learning in material science. As a first step is the data collection. So this is a very interesting graph showing showing when and where the materials data infrastructures were developed around the world. So as you can see, the first one started as early as 1965, and all the databases are still growing every day. So there's a really vast amounts of data to feed machine learning models. Besides data collection, we can also generate our own data. And the first approach is through high throughput computation. This is for materials not available yet in the databases. For example, here we can combine different structures, material structures, and put different elements in these structures to form hypothetical materials. And after we perform the high throughput computation of this hypothetical materials, we can get a vast amount of materials information of the novel materials, and then use it as input for machine learning models. Another approach for data generation is the high throughput experiments. So this is again one example where the experimentalists they designed the different synthesis experiments by combining different precursors for the different materials. And on the right, you can see an actual device set that can do all the experiments automatically, including deposition of the precursors, synthesis of the material, and also characterization to collect the data for machine learning. Then the next step in the machine learning workflow is feature engineering. As I have mentioned, for material science, the features are usually basic materials characteristics as descriptors. For example, the ionic radii, oxidation states, electron negativity. So here, I show one example of the feature engineering where we care about the feature importance. That is, how important some descriptor is to determine the material property. So you can see, you can rank these different features in terms of their importance. And we are also interested in feature correlation. So in this color map, you can see when the correlation is 1, it's completely correlated. The color is in this light brown, and for dark green, it means it's not correlated. So you can see on the diagonal line, because it's the same element, the same descriptor on x-axis and the y-axis. So on the diagonal line is always the light brown color. And the point to do to check the feature correlation is that sometimes two features might be intrinsically correlated by physical law. That way, in that case, we want to remove one of them to avoid the double contribution to our machine learning model. Okay, starting from here, I will give some practical examples of applying machine learning in material science. So first, let me spend some time to explain this material structure called perovskite to you. So this material structure is composed of 3 different elements, A, B, and X. And these different ions are arranged spatially like this, shown in this figure. Alternatively, you can also replace the B side elements with 2 different elements, and they show in this order. That is called double perovskite. So on the right in the periodic table, you can see these different elements are marked in different colors. Therefore, it means they can be put into the different sites. The green for A and the blue for B, and the purple box is for the X site. So you can see this is really a very flexible structure to contain many different elements. And for many, many years, we have been using a factor called the perovskite tolerance factor, which can predict the structural stability of such a structure from the atomic radii of these different elements, Ra, Rb, and Rx. And the expression is on the left, where you can easily see that it's just some geometry relationship, very simple, for this structure as shown here. So recently, in 2019, researchers have developed a brand new tolerance factor that's in the right equation based on machine learning. So this new tolerance factor has been proven to predict the stability even more accurately than the traditional one. But that's not the end. The researchers continued to use this new tolerance factor to predict new materials. So on the right figure here, you can see on the x-axis, there are 59 different elements that can be plausible in the perovskite structure. And on the y-axis are the same 59 elements. So the basic idea is to combine these different elements to put into the double perovskite structure. And by calculating the new machine learned tolerance factor to predict if these elements can form a stable perovskite. And as you can see, the lighter yellow color means the probability is close to 1. So apparently there are a lot of materials, new materials predicted by them. And for the second example, I want to show how machine learning can accurately predict properties. So this is again for the perovskite material we just shown. So here, the authors want to predict a material's property called the electronic band gap. I'm not sure if you're familiar with that. If you're not, it's just some property that can be obtained from conventional methods. But here, the researchers trained their machine learning model from only a little over 200 reported materials. Then they use the machine learning model to predict the same property, the band gap, for over 5,000 unexplored materials. So here, apparently you can see the results from machine learning is very accurate compared to the conventional methods. And once the machine learning model is trained, the prediction of over 5,000 materials can only take a few seconds. So that's a huge difference from the conventional methods, which can take months. The third example is that machine learning can even analyze spectra. So we know materials have different properties, from structure to various functional properties. And to probe those properties, we have different characterization techniques. So XRD spectra is one of those techniques. It is a X-ray diffraction spectra. So it gives you the information on the crystal structure. So the structure, crystal structure, means how atoms are spatially arranged to form materials. Now, what this study does is that they train the machine learning on available spectra that's being obtained from the conventional methods. Then they can, for a given spectra of unknown materials, for example, we have a mixture of several materials and it can be very complicated. Then the machine learning model can identify the components in any spectra like this to tell you what materials are in there. So this can for sure facilitate the autonomous synthesis and the characterization, like I just showed, if you still remember the high throughput experiments. And for a final example is text mining. This is even more magical because in the previous examples, the machine learning model, the input data is based on materials properties themselves. Then in this study, the researchers used the material knowledge in the literature, in the published scientific literature. In specific, is the abstracts of 1.5 million papers. So basically, they're just text we see every day. Then they encode the text as data that's recognizable for computers. In specific, is a vector representation of the human words. So now the text has become data. Then they use the data to train their machine learning model. And then successfully, the machine learning model can capture complex materials science concepts. So it's like the machine understands what's being written in the scientific papers. And then the machine learning can be used to identify unreported properties of materials, or even recommend materials for functional applications. For example, in the right figure, you can see the machine learning model has grouped different materials into for different applications. Okay, so that's the last example. And throughout this presentation, we already get the idea of how the modern day materials research is based on the state-of-the-art data science and computer techniques, which can grant the researchers with the computer skills or very advanced information technology skills. So what does the AI specialization in MSE mean to your career? Apparently, there are many high-paying job postings with high-paying salaries with remote work possible. For example, this one is the company is based in San Francisco, and they are developing the real-world Jarvis from the You Know Which movie, and the salaries is very decent. Okay, so of course it's always good to do further research in the computational materials using all the advanced tools like artificial intelligence. And finally, you can even establish your own startups, like I illustrated here, all the different many AR startups till 2018. So with that, I would like to end my talk, and thank you for listening. Hope you find it interesting.
Thank you, Dr. Lee, for the very informative talk on how artificial intelligence plays a very pivotal role in revolutionizing the way we do research, enabling us to predict the novel material systems for various applications and its applicability to other fields beyond research. So next up, we have Prof. Stefan Adams, currently an associate professor at the Department of Material Science and Engineering at NUS. Prof. Adams' research interest lies in combining both electrochemical and structural operando experimental studies with computational material science approaches to develop advanced energy storage systems such as lithium batteries and redox flow batteries. Beyond research, Prof. Adams is also the secretary of the Asian Society for Solid-State Ionics, co-editor of Acta Crystallographa B, and an active member of several editorial boards. Prof. Adams, please.
Thank you for the nice introduction. In this talk, we will talk a little bit more on applications of machine learning in a particular field, as our group is mostly looking into why do we need better batteries and how does artificial intelligence help us to find them. So if you're at your age, you will not remember a world without lithium-ion batteries, but it's clearly seen how lithium-ion batteries already revolutionized the world. But there's essentially two areas, namely electromobility and the efficient use of renewable energy resources, where the current lithium-ion batteries are not good enough. And we need to come up with better solutions. So you can see this is a kind of overview of, I would say, an old-fashioned electric vehicle. So Tesla is the last company that still uses these very small cells. So we have an anode here, typically graphite, and the cathode material typically containing cobalt. We will talk on this, and then an electrolyte layer in between. And then you see here in this module, we have many of them. We have a cooling system, a battery management system, and then in total, we have thousands of these small cells inside the car. There are a lot of problems with these, especially the electrolyte that is flammable, causes fires. We had this Samsung incident, the Boeing Dreamliner costing billions of dollars. So this university had a nice lineup of new electric buses, started to charge them. 15 minutes later, it looked like that. And 15 minutes later, it looked like that. So all the money was gone. So this was in China, this was in Germany, same thing happened. Also here in Singapore, we have this PMD fires that cost a lot of money and even also cost some lives. When we want to have larger scale batteries, we have more batteries, then we also have to worry about from which elements can we build these batteries. You may know this periodic table, but then there are some corners here. Lithium is limited availability. It would be better to go to sodium, but that's not the worst point. The worst point is here in most of these cathodes, you need transition metals, one of this line, and typically you use cobalt, but cobalt is really supply restraint. So you have to move away from cobalt. People move to nickel. Better, you could go to iron, titanium. That would be the ideal because there's so much available. There's no supply risks. What did I say about the lithium? See here, these are the main lithium suppliers, especially there's this triangle in Chile, Bolivia, Argentina, where it looks like this. You have the brines or the salty water is pumped up from the deserts and then refined with a lot of more water. And that's really a hazard for the communities there that all the water that is available is used for these technologies. Even worse, cobalt. So this is how cobalt mines really look like. And 70% of the world's cobalt comes from such mines, especially in the Democratic Republic of the Congo. So this is certainly not sustainable. So then will go to China and from there refined there and go to the world. People try to limit the use of cobalt, replace it with nickel, just pushes the problem a little bit to the next level. So one order of magnitude more availability, but there's also constraints. And the main exporters in the world of the good nickel resources are actually here in our region, Indonesia, Philippines, and the small islands of New Caledonia. And from there, typically it goes to China and from there then to the rest of the world. And that's why when you compare electric vehicle companies here on the outer fringe, so in US, Europe, Japan, a little bit China, and then you compare now for the electric vehicles who controls the battery technology. So this is China, 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 and then a little bit of Korea and Japan. So there's really shaping how the world economy is changing. Now, how do batteries work? You can oxidize materials, you can reduce materials, and there are some strong oxidizers like fluorine, some strong reducing agents like lithium. Lithium is actually the strongest reducing agent. So when you combine two of them, here copper 2+ with zinc, then you can build a battery from the different tendencies, so different strength of the tendencies to reduce or to oxidize. So the larger the difference is, the larger the voltage will be, and also the chance of having high voltage. So you can see the maximum that you can get is not even 6 volts. So in most applications, you need to combine them. And that was known from the very beginning. Very first batteries here, Volta's piles already had such a stack of these copper zinc batteries. Modern rechargeable batteries look a little bit different. Typically, they have intercalation materials. That means lithium can be stored inside the materials here on the anode side or on the cathode side. This is graphite. This is typically a transition metal oxide. And when we restart it, so when the battery is discharged, the lithium is shuttled from the graphite to the oxide. When it's charged again, then it's pumped back, and that costs energy. When we want to maximize the energy density, then you can see the blue parts are when using graphite anodes. There's only gradual progress, and actually you can theoretically calculate there's a limit here. When you get rid of the graphite as an anode material, which is very cheap, and therefore preferred by the industry so far, then you can go to much higher energy densities, and currently record holder is, you see, NUS. But still, in these batteries, they can only be run for short time. So there's still the problem with getting the better electrolytes that can be stable in contact with both the lithium and the high voltage cathode materials. So in total, when we need to study the batteries, we need higher energy density and power performance. You want to charge your battery fast. You want to get all the energy out again. That's high energy efficiency. You want a long cycle life. That means you want to charge and discharge many, many times. It should be safe, reliable, and even if you're not an expert, nothing should happen. It should be abuse tolerant, and lastly, it should be cheap, and the material should be available so that you can build more and more of these batteries. And in most of these areas, you can expect improvements from going away from the flammable liquid electrolytes to solid electrolytes. That's our main area. So that allows them to use the lithium metal anodes for a long time. That allows to use high voltage cathodes, also allows wider operation temperature ranges. Why is the carbon, so the graphite, a problem? You see here it takes up so much volume. So from liquid electrolyte to solid electrolyte, actually the volume change is small and the weight change is even smaller. But replacing the carbon by the lithium, that really brings in the volume reduction, and that requires that the electrolyte is stable in contact with lithium, which is possible with some solid electrolytes. There's other issues like the so-called bipolar design. So when you have only solids, there's no need for enclosure of each individual cell. You can stack them, just the active materials, which also saves weight and volume at the stack level. You have seen this graph essentially before. So traditionally, people did trial and error, then they try to do trial and error faster with high throughput. But in the end, we are gradually transitioning to a database design. So all these databases you see here are available, some experimental, some computational, and actually 2 of these we have been involved in developing them here from NUS. So with this computational battery design, we want to have 100 times at least faster design of the battery. Then we also want to automatize the fabrication and the testing so that we overall accelerate the development of new technologies. A main tool for that is our SoftBV software suite, where we take data from the materials database, calculate how ions can move in this, then calculate how we can optimize the material by doping it, by mixing in some other atoms, then realize this, make new materials and feed them back into the database. At the same time, we also optimize then our analysis, because always we will, when we do practical tests, we will see some deviations, so we can optimize the way we analyze. This is an example. We had designed a sodium conductor, found low barriers for ionic motion. Then we could make the material test. Yes, it really has very low migration barriers, can really conduct fast. And with that, then we could build a new type of solid state batteries. These techniques are not as good as the density functional theory in terms of accuracy, but they are about 10 to 100,000 times faster. So by the time you analyze one system or one compound by a DFT study, which you should do for interesting candidates, you can study already 25,000 compounds and just pick the one that merits closer inspection. This is an example of an undergraduate project here. Lithium iron phosphate was a very widely studied material. So a very good cathode material. Should sodium iron phosphate be also good? No, it is not. You can show that this requires very high barrier. So 1.6 EV is a very high barrier, no matter whether you use our methods or then use CFD methods. Okay, but that's not the end of the story. Because our methods are so cheap and fast, we can then play with this structure and modify it. For example, we can see what happens when we quench the material and form a glass out of this. Then we get a new energy landscape, much lower barrier, and then suddenly the material becomes a good cathode material for sodium-ion batteries. Similarly, we can analyze when we want to charge a battery faster and faster, then we get less capacity in the battery. That's a law of nature we cannot change in principle, but that happens at different rates for different materials. So with this analysis, we can then easily find out already from the structure of the material at which rate. So this is charging in 5 hours, this is charging in half an hour, this is charging in 3 minutes, at which rate we can still get nearly all the capacity. And this was tested for the same compound, very good agreement. So because the methods are fast, we can also then move on from individual materials to testing entire phase diagrams, entire systems of compound, and say where in this range, so containing iron or sodium and phosphorus, which compound in this range would be interesting. Here the green ones would be, or which electrolyte can be very fast ion conducting. And this is the most promising of all lithium-ion conducting systems. So where does machine learning help us? Where we give a few examples here: coordination polyhedra, or the dopant predictor, predicting absolute conductivities, and so on. In all of them, machine learning was the key to make fast progress. And in most of them, that was using some of our capacities of our students. Okay, you have seen similar diagram from the previous talk. Fundamentally, all of these machine learning technologies, most of them are taken or adapted from image recognition or time series analysis, which may be speech recognition or natural text analysis, some also from financial services. And you always have some data input, some hidden layer and some output. Here it's only in one direction and very simplistic. Then there are more complicated structures. Sometimes you can feedback. So the fifth layer can tell the third layer, oh, you didn't do a good job in filtering. Can you redo and start back, and thereby improve the fitting? And an important one for us, especially for the battery management, is a long short-term memory approach. So that mimics really how we learn. And an important part of learning is also forgetting. So next time when in school you're blamed for having forgot something, so I said it's necessary. We cannot memorize everything. We have to really forget all the details, and we have to learn what is the key ingredient. And that's also the fundamental idea of this convolutional network. Generative adversarial network is a different approach, and it's helpful in the sense of, yeah, you learn how to cheat. So this is the real image, and then the computer will generate, based on what it analyzed from this real image, copies, and you can see whether all the features are reproduced if the user can no longer distinguish which one was the real image and which one was the fake image. So that really allows you to extract what are the important features in a piece of information, not only in images. Okay, very simple example here, also undergraduate projects. In properties of many compounds depend on coordination on the environment of the central atom. So here, if it's very regular, here octahedron, here trigonal prism, so you don't need to know the names, but you can see that highly symmetric, everything fine. But then most of them look rather like that. So how do we classify this one? No idea. So, but we can let the machine tell us. So here, another case for the fourfold coordination. So we need to come up with proper labels. So we are called classifiers from database entries. And then we need to find the descriptors that help the machine to learn which of the environment follows, should have which label. And it turns out in this case that the first guesses that the researchers had were not the best ones, and we have to come up with much more complex descriptors. And so we offer a wide range of descriptors and let the machine then reduce the features. As already told, also we need to have a training set. Very often you don't have the luxury of having millions of data, so you often have only limited training set, and then you may use a lot of your data as a training set, but you should always reserve a part to have this independent test set you never used for optimizing, and still in the end, it can be labeled correctly. Another example here is our dopant predictor. So how many foreign atoms can you dissolve in a crystal structure? So we offer a lot of descriptors, and the blue ones are the ones that are selected by the program, and we could come up with a good correlation so that the predictor can really tell how much energy would it cost to have this doping. Actually, this was published early last year. You can see none of these people are still with us, so they are snapped up by all these companies after having completed their studies. So both, one was undergraduate, the others are a PhD student. So you can see here that will tell you which compound. So in a compound, where will the ion go, or it can tell you how much of the ion can be dissolved, all from this simple machine learning tool, which allowed us then to come up with, again, a rather good battery. So these authors now, one is advising the Indian government on research projects, and the other one is now in the Chinese Amperex company, that the biggest battery manufacturer. I think the last of these type of projects are in the conductivity. Very complex formula, actually not so difficult. All these black parameters we can rather straightforwardly calculate when we have a structure. But this is the correlation. When one ion hops, will this push another one to also hop? This is very hard to calculate, so many influencing factors. And again, this undergraduate student could come up with a good formula how to predict that, and that gives us then our connectivity. If we want to predict devices, you have to do more than one individual material. We also have to see how materials work with each other, so how they interact, and often we need then to combine the DFT simulations with our energy landscapes. So we started from this, then expanded this to this empirical system where we can really follow over longer time scale. And that also led us to come up with a machine-learned new force field. Again, actually this started as a research track student assignment, then become an MSE master project, and now we can use for all these complex simulation tasks. Of course, there are machine-learned image recognition problems also in material science. So here, this is in batteries. We have to see, are there any defects in these batteries, very similar to this track analysis problem, but more for material science, and then can let the program learn, and then it will tell us, oh, there's a problem in this particular battery, and so this one should not be delivered. In battery management as well, maybe we don't go into the details here. What is the state of charge of a battery? It's not only how much energy you put in, it also changes with the aging of the battery. So you need to have a complex problem where machine learning is now routinely used. And we also have an ongoing project where there are opportunities for MSE undergraduate students on determining the state of health of a battery, because many batteries that are no longer good enough for the use in electric vehicles can still serve for stable power supply in stationary systems, but we have to select those that are still healthy enough. Yeah, and we cannot cycle them forever, that then we kill them. So we have to quickly come up with a judgment. And that was the last example. And with that, I have to thank you for your attention and thank all these people who really did the work.
Thank you, Prof. Adams, for the very interesting talk on the importance of identifying promising and novel material compositions for energy storage to meet the world's demand for energy, and how you and your team have used artificial intelligence to facilitate this process. now that we are done with the first part of the webinar, and on behalf of the organizing committee, I would like to extend our heartfelt gratitude to the speakers for taking time on their very busy schedule to attend today's session. Thank you also for making today a webinar success. To the audience, we hope today's session has been a fruitful one for you, and we look forward to seeing you in our upcoming session. And the next one that is coming up is on electronics, to be held on the 26th of January. Do scan our QR code to sign up for this session. And if you have any questions pertaining to admissions, you may connect with our admissions advisor using the QR code. And if you have any questions, you can also write into our Prof. Adams and Dr. Yuhan. You can Google them on it.